We had a special request during this morning's review to do an oxymercuration mechanism with labeling. So we're going to do that, special edition. This is not on any old exam. I made it up just now. It's got the same format. You're going to do a mechanism for the reaction below. It's worth 10 points. I'm going to get my picture out of the way. I'm going to explain, circle the major. There is no major. We had to get rid of this. There's no major in this. There's only one product. So, yeah, I can't do that. There you go. So, oxymercuration of an alkyne is what's going on here. There's the mercury. Mercury in chapter 6 and 7 must react first. It's the mercury. And that's only one arrow making this triangle. So we've got this triangle. We can go like this and then partial. One arrow means you've only got partial bonds all the way around. And the plus is on the mercury. And the other plus, because there was two pluses to start with, shared. And I don't need to show these H's here. Stick figures. I know there's an H there and an H there. After you make a triangle, anytime you make a triangle, next step, backside attack. You're going to use the water. That's how you get the O on there. So we got the water here. Got a lone pair on water I can use. Coming around. No, that's a green arrow. I don't want a green arrow. I want a red arrow. Where'd my lone pair go? Red arrow. Backside attack.
Does it matter if it goes to like the top one or the bottom part?
I don't care as long as it attacks the carbon. Okay. There. I'm having trouble getting rid of stuff. This won't go away. There. All right, here we go. In normal circumstances, it would go to the more substituted carbon, like you said. But in this simple alkyne, which is now an alkene, it's got same substitution on both sides. So you pick one of the carbons. I picked the one on the right because my molecule has the oxygen on the one on the right. It'll be easier to see visually how the oxygen got there. But you don't have to pick the right or the left in this example. And let's see what we get here. You still have the double bond. The water came in from underneath. So it's down there. The mercury gets all of the electrons that were in the partial bond now end up in a real bond. That's a real bond. And mercury's still +1. Notice the species is still +2. It's got two pluses. +2 here, +2 here, +2 here. And now we got to neutralize our oxonium. Neutralize the oxonium. I could use water, but it's not really the best base. I'd be pretty forgiving if you used water and probably just dock you a 1/4 point. Sulfate is a little better of a base. Even though you don't know the pKa of hydrogen sulfate, it is a little bit better base than water. Just remember, sulfate does get used. It's not just there being an ion for the mercury. So sulfate we'll put in purple. We got OSO3 lone pair. Oops, it's sulfate, not hydrogen sulfate. Sorry about that. It's the one above the arrow right here. I copied it. And then neutralize the oxonium. How many times have we neutralized oxonium in this course? It's got to be 15, maybe 20. I don't know, more. Okay. So you get hydrogen sulfate. You got HO. It's a side product. I don't even know if I really need to see this. Maybe if I need a base later, I can use that one. Move my picture. And more importantly, the organic thing. You got your mercury. You got your bond. You got your double bond. Oh, it's an alkene attached to an alcohol. Yes. So eventually we're going to undergo tautomerization. Enols are never final products. Next step is the P word. Protonolysis. We got to use that sulfuric acid, which surprisingly hasn't been used yet. Strong acids that aren't used until step 4, pretty rare. So let's use it. Protonolysis using sulfuric acid. We have sulfuric acid in purple. Maybe, I don't know, hot pink, why not? HO3SOH. Carbon keeps the electrons to make the bond. I don't like that second arrow very much. It didn't clearly start on the middle of the bond. Now it does.
What is like the arrow, you know, if I want a stick figure, attack the H.
The bond is kept, the electrons in this bond are kept by the more electronegative carbon and used to make a bond to H, and the mercury goes back to being mercury 2+. I don't need to see this side product, but I'm just reminding you, mercury 2+ is actually a catalyst. And carbon got the H. I'll put the hot pink H on there. You don't have to show me, it's stick figures. Protonolysis, mercury gets replaced by an H. That's right. You still have your enol. That's your enol. You don't have to tell me it's an enol, but I'm just trying to remind you. It is time for the old, equilibrium called tautomerization. And you need an acid-base pair for every tautomerization, conjugate pair. The best pair we have here is sulfuric acid again, and its conjugate base, which is right here. So I'll redraw both. We got the conjugate base. I'm going to put it, I don't know, below the arrow, above the arrow, it doesn't matter. Conjugate base is HO3SO minus, and the acid is HOSO3H. During tautomerization, it's always the same. It's easier to remember if you always start with the base taking the proton off the alcohol. No matter what tautomerization you're doing, use the base to take the proton off the alcohol. Then the sigma between O and H becomes a pi. That's going to be a carbonyl. In this case, a carbonyl that's an aldehyde. And then the pi that's there picks up a proton from sulfuric acid. Sulfuric acid's a catalyst. You used it here, and you made it here. And the labeling is going to be cool. And just a reminder, we do have an aldehyde when we're done here. Aldehyde. That doesn't sit well with some of you, because you learned, you memorized. In fact, it's part of question D. You memorized, because memorizing helps you sometimes. Memorizing without understanding is not help at all, ever. That's where mistakes are made in life. Most of you have probably memorized this fact in quotes, because it's not a fact after you read this. Oxymercuration protonolysis of alkynes gives ketones. While this is normally true, explain why it is not true in the reaction below. I mean, you get a point just for saying it made an aldehyde. Okay? You get the rest of the 2 points by saying ketone's not possible in a molecule with 2 carbons. Go ahead, try to draw one. There's 2 carbons. You're going to put a carbonyl on one of the 2 carbons. That means it's on the end. Do ketones have a carbonyl on the end? No. They have carbonyl with 2 carbons on each side, 1 on each side, sorry. 2 more carbons, 1 on each side. So we're going to have those words written down eventually. Okay, now where am I at? It's time for Lubnu Habibi.
Oh, you're making us do that.
Yeah, on question 1 of the short answer, apparently, because it was promised.
That's fine, fine. So they're easy.
Yeah, start of arrows is where I always start. Let's go with orange label.
Lube, is synonymous with nucleotides.
Correct. You always put lube with nu. Then anything where the arrow begins is a lubnu. Anything where the arrow ends is an ELA. Yeah. If it attacks a proton, the lubnu is also a Bronsted base. It did not attack a proton. Do not put any Bronsted on these labels. Similarly, for the next step, the originator of the arrow is a lubnu. It's water. The acceptor of the electrons is always an ELA. Love it. Loves electrons. Oh, that's another way to do that. Misspell electrons. Loves electrons. Or just say electron acceptor. LA. Electrophile is electron acceptor. Loves electrons. All right, now I see protons in the next one. Originator of the arrow is the lubnu, and it's attacking a proton. BB. The thing attacked is always an ELA. And when it's a proton getting attacked, it's a ba, ELABA. There you go.
How about the bond going to O? Isn't that, you want to mark that too? Like,
Oh, no, that's not 2 molecules reacting. No, it's only when a molecule hits another molecule with electrons that you put the lubnu. And that's just arrows compensating for this new arrow here. This compensates. And it's all about Bronsted here. Originator is the lubnu. So this guy is the lubnu. Oh, orange. Lubnu. And this guy is the ELA. That's an L. ELA. And it's attacking a proton, so the lubnu is a BB. And the thing getting attacked is a BA, Bronsted acid. It's got a proton. Now, if you look carefully at the tautomerization, there's 3 molecules involved. 3. So a label for the originator is the base there, isn't it? It's a lubnu. Lubnu. Is it attacking a proton? It certainly is. So what else is it? A BB. Now go down to the area where there's a proton being attacked and just say it's an ELA. And it's a proton being attacked, like I just said, so it's also a BA. And then there's another attacker. This is attacking a third molecule. So where it's the attacker, this portion of the molecule is acting like a lubnu. This portion of the molecule is a lubnu. It's attacking a proton, so it's also a BB. And the thing getting attacked is an ELABA. It's getting attacked, so it's an electrophile, synonymous with Lewis acid. And protons being attacked, it's a BA. There's 6 points of labels for the tautomerization. Wow.
yeah, that's what it's doing.
I know. Just the labels. 1, 2, 3, 4. And then 3 more, 7. And then 3 more, and 10. And then 3 more just for this triplet. is 13, and then 3 more, 16 points for part C. B, 16 points. No, oh, yes, proteinolysis for your purposes, for your knowledge or base right now, only happens in chapter 7 with alkyne. Because it does, but we have never learned a reaction where alkenes does it. So I'm not saying it doesn't happen with alkenes. It just, we don't teach all organic chemistry. We teach the fundamentals. Proteinolysis is a very broad, general thing. But for keeping track of what you need to know, it's important because you're a college student. So for your knowledge base right now, proteinolysis happens here, right in this step right here. That's called proteinolysis. And with hydroboration in the presence of acetic acid to make a cis-alkene. There was a proteinolysis using acetic acid in that one. Yes, sir.
So this is the one you start with on that hand. It's like 20
Yeah. This is a nice place to start to roll off some quick points. Yeah.
Is this gonna be very similar to the one on the hand?
Yeah, or the one we did on the review day. You guys, I think we did it together, didn't we? Yeah. Review day Monday. We did question 1 from fall 19. If it wasn't your section, it's the other section, and you're looking at those notes, you promised me. Nobody in this room is saying, oh, he did it in the other section, he won't put it on the test for us. You're not saying that, are you? No. They have the exact same study guide. They're getting I can't say they're getting the exact same test, but they are. That's why you're signing that document. You'd be foolish to cheat and say, you're hurting yourself. If you think about it. But why cheat anyway? Cheating just scares the crap out of me. You guys want to be doctors. This world's tough enough without knowing there's doctors that got into medical school by cheating. Because they won't stop. Anyway, I get all flustered. I think I've made this speech before, right? It's on the syllabus for crying out loud. Yeah. Yeah. You remembered it stuck. Good. Well written then. Okay. Did we finish? Oh, we have to comment on that fact. So let's just do a sentence that covers why this deal made an aldehyde. Control T. When there is only 2 carbons, it is physically impossible to make a ketone. I think that covers it, right? And that was,
You won't give us one with like 2 products, would you?
yeah, I did in the review one. That's why I'm doing a different one now.
Are you sure you did something like exactly? It was probably number 1, like with the question.
I took the fall 19 question and started this document from it. And that one had 2 answers. And then I just changed the reaction. There was an oxymercuration in that one too. It was where in one step we took a proton off the alkyne first and put a deuterium in its place. If you're not knowing it now, it's because it was the other section, and you'll see it in the video. You'll see it's the same wording on the top. It doesn't have a part D because that one did have an aldehyde and a ketone.
You gotta pick which one you need.
And then you got to pick the right one. And I'm going to make this so we can see this. Right now. Right now, people are watching the video and going, they're falling asleep. There we go. D, when there is only 2 carbons, it is physically impossible to make a ketone. I like this answer. Save, and that's it for this. I hope.